by Sergei Sharapov. We'll talk about the density of states in graphene in process magnetic and E-plane electric fields.
Okay. So I would like to thank the organizers for an opportunity to participate in this beautiful and nice lesson offline. And okay, yeah, it's working. So I realize that the subject of my talk is not ultramagnetism, but actually, as you will see, we are going back to the first principles related to actually Landau diamagnetism, and I am going to present results from our recent work with our pharma PhD student, with our bachelor students and our postgraduate student, Andrei Chaika, Elizaveta Kulinich, Dmitry Orechov, which were published recently. So the outline of my talk is the following. I will remind you what's the difference between Schrödinger and Dirac-like Landau levels. Dirac-like Landau levels are realized in graphene. Then I will just mostly for pedagogical reasons, discuss density of states in the cross electric and magnetic field in two-dimensional electron gas, discuss what we have for density of states in cross field in graphene, and speak about possible interpretation of this result and discuss consequences. So a brief reminder that actually although we say Landau levels, actually they were firstly theoretically discovered in the paper by Rabi in 2 years before Landau, and Rabi considered Dirac equation, and later on Schrödinger case was discussed by Matvei Bronstein and Frankel, and then came this famous Landau work, but you will see actually we will discuss exactly what is specific for this work. So the difference between Landau levels in both systems, that for Schrödinger case we have this harmonic oscillators equidistant staircase, so dependence on magnetic field is linear, and for Dirac-Landau levels we have square root dependence on magnetic field and zero field independent Landau levels. This what I show is, of course, for solution for an infinite system. And also, just to explain in the basic physics why graphene is exciting, I remind you the following circumstance, that if we use 3 electrons, field of 1 Tesla creates difference between Landau levels approximately 1 Kelvin. For graphene, 1 Tesla creates 420 kelvins, and this is the reason why this physics of graphene and magnetic field so much exciting people. But in my work, I'm going to talk about more complicated case, and the rest of the work will be that magnetic field is perpendicular to the plane of two-dimensional material, and in addition to magnetic field, we have in-plane electric field. This is the main formulation of the problem for both system, two-dimensional electron gas and graphene. So also for two-dimensional electron gas, this is Landau level is the textbook problem, that distance between Landau levels is preserved. Also the energy is slightly shifted. And the main thing that energy spectrum acquires another quantum number if this is momentum in direction perpendicular to the electric field. And how do we calculate density of states? Of course, we have the basic definition. If we calculate those density of states per unit area, and I ignore spin splitting, we have to sum this delta function over all quantum numbers. And our quantum numbers, as I said, this is n and k1. And area is a product of sizes of the system. Obviously, in the absence of electric field, I come back to Landau level case, and let me remind you how Landau solved this problem in paper from 1930. He essentially used this position wave vector duality, that this momentum ky corresponds to the center of the orbit. So instead of summing over wave vector, one can sum about the center of the wave package. And it's known that actually this density of states is ill-defined. So what I mean that Landau, to solve the problem, actually put the system in the box so that he assumed that x naught is between I use the position minus Lx over divided by 2 to Lx divided by 2. And then this contribution gave this famous Landau result. And here comes this, so L small, I did not say it, this is the magnetic length, and here comes this famous degeneracy factor which we use in the textbook to teach students. That this degeneracy comes, we essentially measure magnetic field in the units of magnetic flux. And actually, this is what most of the textbooks, if you open Landau textbook and many, this is how we teach it. And if you look deeply history, and there is very nice, for example, this textbook of Haidu. And if you look history, it was Edward Taylor paper who actually realized that the consideration of Landau was not complete. So you see actually mathematically what happens. That we, following Landau, we use the solution for an infinite system. And obviously we put it in the box. And there is this inconsistency which was solved by Landau. And if you look at these papers, actually, if you calculate magnetization in this fashion, you are in trouble. Landau, the specific of his work, that he calculated thermodynamic potential, so he avoided all this problem. All this is written in this article of actually Haidu with an MSc student. So what we do if we go to the crossed fields? We can formulate the problem in the same fashion, so that we from Ky to go to the center of the orbit, write the energy in two-dimensional electron gas in this form, and then calculate the density of states for the crossed field by this integration of density of states without electric field. Okay, and so obviously for clean system we have the difference of two theta functions, and when we started to think about Dirac problem, we immediately discovered this nice paper from Zavadsky from 1997-99, that this is the density of states in arbitrary units, and here is the energy, and actually, obviously, you see that depending on the value of electric field, or actually this control parameter, which I denote gamma, is the energy of electric field. So we consider, I stress, the system that electric fields is absent outside of this region. So actually, we enhance this inconsistency of Landau. Actually, that I continue to use Landau levels for an infinite problem, but put them in the same kind of the box. So that this U is this energy of electric field divided by magnetic, and we have a widening of Landau levels. This widening, I stress, is not due to impurities, but due to because all levels are shifted by this Ky. Okay, and one can play with some mathematics, introducing some finite Landau level width, and actually to calculate this dose in terms of d gamma function or derivative of gamma function. You see, the derivative is convenient because we have integration. And so to obtain this expression for the dose in the presence of impurities, and you see that without electric field, this is expression, that in the limit of zero magnetic field, I recover free electron, dose of a free two-dimensional electron gas. And if I use density of states in the crossed field, I have an interest in an energy intermediate region. You see, we know that two-dimensional electron gas itself is without fields, is constant density of states. In when the electric field is left, there is this linear term appears in energy. So like this step. Okay, so I so much explained it, the basic things, because for Dirac fermions in graphene, you will see the surprise. So let me explain how Landau levels for Dirac problem look like. In quant, so there is this term proportional to the wave vector in plane perpendicular to electric field, but there is another. So there is this non-equidistant staircase of square root, so magnetic energy scale for Dirac fermions is square root from magnetic field, and there is this factor beta, which is the ratio of electric field divided by magnetic field, and we have the Fermi velocity of graphene and velocity of light. So I use SGS units. And the specific is that when beta goes to 1, all levels shrink to 1 point. And actually, this is the reason why we found this problem interesting, although the bands are not flat in a sense because the dispersion is conserved, but we were actually thinking about some phenomena which appear when you have enhancement of the density of states. This is a physical reason. And actually, this is a Landau level collapse. There is a bunch of literature, and there are claims that it was observed experimentally. And how to generalize density of states for Dirac fermions. And here is the surprise comes. So the first thing that I did not put the reference in the talk, but they are in my paper. The first thing is to write equation in the same fashion as was written for two-dimensional electron gas to put the degeneracy factor from Landau. Yeah? But apparently it's not. The main statement of my talk is that for Dirac fermions, this non-equidistant levels in crossed fields, the degeneracy of Landau levels actually is dependent on is a product of like Landau level degeneracy by this, in some literature people call it relativistic factor, but actually there is some reason to call it, but in any case, this is a ratio of electric and magnetic field. And the remaining part of my talk that I actually, when we discovered this, I look at all possible literature, discussion in the relativistic physics, and I did not find any statement in the literature except there are a few papers which studied thermodynamic of Dirac fermions in the crossed field without this 1 over beta. So the rest of my talk, I'm going to argue why we are correct. So
it goes to 0 when it collapses, yeah?
Okay, so this degeneracy goes to 0, yeah. When there is a collapse of Landau levels. And intuitively, there are some reasons to understand it, but I will show you some proofs. So first of all, one can just play plotting the Landau level similar to two-dimensional electron gas, introduce the parameter gamma energy in electric energy divided by magnetic energy, and you see the situation is much more complicated. The levels are not equidistant. This parameter does not allow to say that there is this electric field dominated or magnetic field dominated regime because at some energy the levels start to overlap. And here we played that firstly 2 levels overlaps and 3 levels overlap. So actually there are so many interesting things to play for experimentalists doing, for example, tunneling spectroscopy. And the parameters gamma, which I introduced, and beta, actually, beta is the ratio of electric and magnetic field, are not independent. And actually, if you want to keep gamma constant and beta change, you better change the size of the system, for example, or something like this. Okay, so let me firstly provide you analytical arguments. So this is the density of states of graphene in the absence of impurities, or for those who work in superconductivity, immediately realize that this is the density of states of D-wave superconductor in the node, linear in energy, that's it. And what we obtain, I did not already explain the mass, I give the final result. So we put problem in the crossed field, and then add impurities and then put a limit of disappearing in magnetic field. This density of states modifies in the following way. So it's for energies above this electric scale, it's still linear, and inside it's replaced by the parabolical one. And here is the first analytical argument why I claim why we have to modify the density of states. So actually, if I omit this factor here, I would actually, in the opposite, obtain divergent density of states as this beta goes to 1. And I would not recover behavior of free density of states. So this is the reason why, so this factor for me is crucial to modify it. And interesting physical analogy about the role of this perpendicular electric field. Again, another result which for me goes back to the wave superconductivity is the presence of impurity. We know that impurities result in the finite density of states in the node. For the wave superconductors, this was widely discussed. For me here, the same job does this perpendicular electric field. And from correspondence with experimentalists, I realized that they are interested in using electric field for controlling this behavior. Okay, so this was an analytical result, and actually another is numerical consideration. So what we did with this quant package, we numerically solved this Edward-Teller problem. So what I mean by this, that we calculate the energy spectrum for the system with for zigzag nanoribbon in electric field, and we reproduce spectrum for this is the spectrum for this work. So you see that this is exactly what was Edward Teller suggesting, that let's to avoid inconsistencies of Landau problem, let's put the problem in the box. Here is the density of states. And okay, you see that because to reach the result, one should apply huge magnetic field for numerical calculation. But okay, if we what we can do numerically, we can fix this parameter gamma, this is ratio of electric and magnetic regimes, and change beta. And you see that actually all so here color curves are numerical simulation, and this is not noise. Those are Landau levels that match. And this black curve is exactly this. So linear outside and parabolic inside. And you see that numerics collapses to the same. So it shows that this factor 1 over beta square in power 32 is also absent. So so we believe that numerically we reproduce this result. Okay, how to understand this result? Let me explain you interesting approach for discussing basically Landau level problems in a crossed field for graphene. So that we know that graphene is discussed by the Dirac Hamiltonian, where if we just have electron term, role of speed of light is played by the Fermi velocity. Okay, so let's so we have very strange world that it has usual electrodynamics, but play role of speed of light is played by the Fermi velocity, and here this is gamma is another, so this is Lorentz factor. So you see Vf is the speed of light, and if I go to the frame which moves with the velocity v, my electric and magnetic field are transformed in this way. And you see that for when v is equal to v naught, which is actually drift velocity. In fact, this is so another way to understand collapse of Landau levels is to think that this beta corresponds that v naught is the drift velocity. Then in this frame, electric field would disappear, and magnetic field is renormalized by this factor. And since Dirac equation is Lorentz invariant, we have Landau, we map the problem in the crossed field We map to the the moving frame. We map the problem with just magnetic field, but for smaller volume. So we have Landau levels in this frame like this. The energy for me is the zero component of energy momentum vector, and if we do the inverse boost transformation, I would reproduce this result for collapse of Landau levels. And basically, this is discussed in these papers which I showed you. This is from 07. This is the very first paper where Landau level collapse was discussed. So if I recall relativistic physics, the true invariant for relativistic physics is actually this one, h square minus e square. And this is, I believe that this is probably the argument why in my case this is what happens. And as usually dig in the literature, in this paper from 2022, we discussed discussion of the system like this in Soviet jet from 60s, but I did not see this degeneracy factor. So to summarize, that our claim that for graphene in crossed field, this Landau degeneracy factor for correct consideration should be replaced by this, and the implications are obviously not only for thermodynamics, but basically all transport on graphene in crossed electric and magnetic field should be considered using the correct degeneracy factor. And from correspondence with Mark Gerbig, we realized that actually there is another story of studying of so-called materials with tilted Dirac cones. This is another kind of materials, and he believes that the same effects that as we expected should be also seen in this material. So thank you very much for listening.
Sergei, questions from the audience session?
Why beta is not possible to be larger than 1? Why can't be larger?
It's actually possible. I mean, experimentally, theoretically, it's possible. But just physically, those are completely different things. That beta less than 1, we have Landau levels. And beta larger than 1, this is the so-called Schwinger regime when electric field is dominated. So this invariant changes the sign. It's actually...
what means negative degeneracy then?
No. Already no Landau levels in this case. So this is another story. Julian Schwinger suggested that large electric field in relativistic systems can create electron-positron pairs. And so
okay, but when it's 1, I don't understand how it looks like. So Landau level, they all are in 1 level.
They collapse.
Collapse. Yes. They're in 1 level. To 1 level.
Yes.
Why zero degeneracy? Where are all the states then?
But there is no discrete levels. The levels are unstable. And actually, since you raised this question, I can give you intuitively how this degeneracy factor is understood, at least in the way how I realized how to teach the student. That you have Landau levels that have distance proportional to magnetic field. Okay? And then if you ask what is the degeneracy, you of course should put all states that were in the free reluctant gas on 1 Landau level. So the reason why this proportionality like this. So if you have collapse, if the levels are getting closer, so this is another reason why this factor appears, because the levels are getting closer.
Each one has degeneracy goes to 0. But for the whole of them, since they're infinite, the degeneracy
but this is exactly how actually, if you since this is how this mass works here. That actually the beauty of this approach of doing the sum in terms of this of the gamma function, if you introduce some infinitesimally small width of the levels, you can play and see, for example, how you recover from this expression free electron gas. So you can do it even analytically, exactly to answer your question.
Okay. For each one, the degeneracy goes.
Yeah.
I have a small question. So the very nice results. So you showed the band structure or the energy levels as a function of Ky from quant. Can you go to this slide? Yeah. So this is non-reciprocal in the sense that minus K and plus K are different energies, right?
Yes.
So, yes. So my question would be, if I put the Fermi level at 0, then probably the system has a finite momentum, a finite total momentum. Or if I...
Okay, this I do not remember that. Normally, if you introduce both K points, somehow the symmetry is always recovered.
So this is at K and at K prime. You mean
here you see, because this is already lattice, both K points came. So there are 2 K points actually.
Right.
But I do not remember that people were discussing the finite momentum. Well, at least what can I say that in this respect, our simulations are in agreement with this. I omitted completely the story that this is the zigzag age. Armchair age would actually be different. And what I can say about zigzag age, and I did not say what about this. There is also this dispersionless mode emerging at the age and so on. But I mean, maybe we should talk afterwards about it.
It's interesting, yes.
Other questions?
Slide number 5. A question concerning a limiting case when a magnetic field tends to 0. Magnetic length when magnetic field tends to 0 tends to
infinity.
It is infinity.
Yes, and then the degeneracy factor would go to 0. This is probably correct.
And the same for the spectrum stage to 0.
The levels merge. The levels merge. So that well, this is what I see here analytically. This you can go with magnetic field to 0, and from this to come back to two-dimensional electron gas. So the statement is the following: that if levels are separated, each level picks up the states that were in between levels. Then the levels getting closer, so the degeneracy of each level becomes smaller and smaller.
Okay, I see. Thank you.
I want to ask a question. You QED, you do those Euler-Heisenberg calculations of electric magnetic fields. Then in graphene, you are in 2+1 dimensions. Then how this can you, if I use this density of states, integrate out diagonals? So what is do you know what the Euler-Heisenberg result would be?
I know what is it, Euler-Heisenberg.
Yeah, I know. When you ask if you know the result, which result you would get with this.
Actually, maybe I will not answer precisely your question. This is what we are asking. That one of the problems to work. Yeah. That there is this actually this intuitive Landau procedure how he got his degeneracy. Another way you can construct Green's function, at least in magnetic fields, by the Schwinger method. And if you mathematically, if you integrate over momentum, then you will recover the normal degeneracy effect. So this is probably mathematically the most correct way to not to follow Landau way with this intuition. But what we actually looking is what happens if you have the problem in crossed fields. This is somehow it's a little bit tricky. But actually, our postgraduate was looking at this. And I would put it like this. I also look at the bunch of the literature related to relativistic problems, because if you forget about graphene, you may think about problem of, I don't know, neutron stars with in crossed field. And I was asking what they write for thermodynamic potential. I did not find. Because for me, all problems for relativistic thermodynamics probably should be also using the generalized factor.
Yeah, it's curious that there is nothing in the literature about this.
Well, I had the hope that one of you will say that I'm wrong.
Okay, so there are no further urgent questions. You can ask also during the coffee break.
Yeah.
So thank you very much.